Okay, so we are all set. This is the first lecture in error control coding, which is EE5120 according to our new numbering system. Hopefully all of you are in the correct class. I guess it's a recording studio, so you wouldn't have come wrongly to this class. That's not a problem. Okay, so what is this course about? This course is about error control codes. If the whole entire the terminology is new to you, you should seriously rethink doing this course. I'm assuming you have enough background to know what error control codes are. Okay, so those are some serious prerequisites. So I'm going to start this course by talking about prerequisites. This is particularly important. Please pay attention to this. Okay, so the things that I am going to list down now are very important for you to get a good grade in this course. Okay, so by a good grade I mean anything other than you. Okay, it's a good grade. So if you are if you're not sure, if you have not done well in these courses in the past, very seriously reconsider being in this class. Okay, so what is it that I'll assume that you know? I'll assume you know probability. Okay, not spelled it correctly. Okay, you can see what it is. So I'll assume you know probability, random variables, random processes. Okay, so I will not do that. You will need to know it at a fairly good level. Okay, so for instance, in the previous courses, 356 for the undergraduate students and say 511 for the graduate students, if you got less than a B, okay, it's a very high chance you will get a U in this course. Okay, so think about it very seriously before you take this course. And in the past it has happened, particularly with BTech students taking this class in large numbers like it's happening now. There was a significant fraction of those students got a U. Okay, and after a lot of pleading I did not change anything. So this is a very serious warning for those guys. Okay, I know you are doing several other courses, you will not be very sincere in this. If you keep doing tutorial sheets 2 days before the exam, you're in big trouble in this class. Okay, it's not like the previous classes. Many things you're doing in this course you would have never seen before. Okay, so it's a serious warning. Take that very seriously. I think other people will be largely okay. Okay, it's not a problem. So probability is one thing, and the other thing I'll require is linear algebra. Okay, so this is one more thing that I will assume to a large extent. So usually it turns out that most people think that they know linear algebra. When you see linear algebra, I know exactly what it is, there is no problem. Usually that is good enough, okay, more or less for this course at least. Okay, we will not do any very serious linear algebra, but it is good to know at least some things very well. Okay, so for instance, if you have done the mathematics linear algebra course, you should be okay. Okay, otherwise you might need some reading up. Okay, again I will not have time to go into linear algebra at depth in this course. Okay, so that is another thing I will not do. Okay, any specific questions on these two things? You are okay? Alright. So another desirable, though we won't really need it extensively and I won't assume this too much, is a course in digital communication. Okay, so I understand a few of you might have already done this course, maybe a significant fraction might have already done a course in digital communication. Maybe there is also a significant fraction which is maybe doing it now. Okay, doing it now should be also okay. Okay, if you are not doing digital communication at all, what will happen is half the time you will not understand the motivation behind what I am talking about. Okay, I will just introduce something and I will keep on talking. It will make sense maybe as an independent entity, you may not be able to relate it to the practice of digital communication. Okay, so it's good to have done this course, or you should be doing it this semester. Okay, so for the undergraduates I think there is a 419 which you should be doing, or I think for graduate students there is a 611 course. Okay, if you are doing this in parallel, it's okay, it should be okay more or less. Okay, so that's the prerequisites, and like I said, I am starting with prerequisites, not with the intention of scaring you a little bit. Okay, so don't take it lightly. It's quite important that it's a fairly serious course. Okay, and in general there are some aspects in this course which will require so for want of a better term, a reasonable amount of mathematical maturity. Okay, it is impossible to define this very precisely, but I am assuming you will know what I mean. Okay, so things like theorems and proofs should not scare you too much. If you make a statement and I try to prove it, you should know how the proof is working, okay, more or less. Okay, for instance, one of the standard things that is done to show one set is equal to another set is what? How do you show that? Yeah, so you start by showing one set is a subset of the other, and then you show the other set is a subset of this set, which means these two are equal. So things like that are, there are more complicated versions of this. I am just giving you a simple example. If you have never seen any proof where that was used before, you should be a little bit scared of this course. Okay, so you might get seriously left out. Okay, so for instance, the problems in quizzes will involve proofs like that, and I will expect a precise proof. You can't just say, oh, intuitively this is clear, so it's the answer. Okay, it's not acceptable in the exams. Okay, so for instance, in 356 for several questions people answer like that, and probability you just say, oh, intuitively these two are independent, so you multiply and you get the answer. Such things will not be possible. Okay, so you should get used to it, primarily for the purpose of answering questions, writing it precisely, what are the arguments, how one follows the other. Okay, so those things again I can't do in this course. I am assuming you are comfortable with them. Okay, all right, everybody is with me on this. Okay, so that is all about prerequisites. I guess that is filled out one full page already. I'll go to the next page and I will give you some administrative informations. The first thing is the website for the course. The course web page is hosted in Moodle, the EE department's Moodle. Okay, so if you have not heard of this website, just write it down, go visit this web page. There will be a login there. You have to log in with your SMail login name and password, and then you have to click on E5120 error control coding and you have to enroll. Okay, the enrollment will probably be open for the next 1 or 2 days. After that I will close the enrollment. Okay, so if you do not enroll within the next 1 or 2 days, you will not be registered as someone who is doing this course, okay, which means you will not get a grade. Okay, so make sure you register, it is important. Okay, I will put up some information here. The assignments will be uploaded on this website, the grades will be available through this website. What else? There is a forum which you can use for posting messages if you like. I know it is not the most popular forum in the world, but something you can think about in case you are interested. The TAs will also be registered members of this web page. I can't see the TAs anywhere here, so they might be, they will also be members of this web page as well. So that brings me to TAs. We have 2 TAs for this course. One is Vinay Praneeth. Both of them are not here, so hopefully they will show up. I think they have registration or some such thing today. So we'll see. The other person is Rakesh P. Okay, so these 2 guys are the TAs for the course. You are free to approach them. I am assuming you would know how to contact them. Both of them are 5th year dual degree students. Okay. Right, so both of them are 5th year. Looks like the display driver is giving me some problems, but it is okay. 5th year dual degree students, so they will be available, they will be in the lab also. So in case you need to contact them, you can email them and find out who they are. Okay, so that is TS. And about exams, there will be 2 quizzes, quiz 1 plus quiz 2 plus finals. There will be a very simple weightage, 25%, 25%, 50%. Okay. So there are no, I mean, for instance, in the past I have given some tutorial exams to help out people who are not doing well. In this course, there is no place for such things. Okay, so I am assuming you are going to do well. Okay, so that is my assumption. You are interested genuinely, you will attend every class, all these things you will do. Okay, so those are assumptions that I made at the beginning of this class. If you are not going to be following up, then you will be in trouble. Okay, so it's just 25%, 25%, 50% in the finals. Okay, and what else? What else? What else? Okay, so the Moodle web page also has information on the syllabus, outline, lecture-wise split of what I'm going to do in each lecture. It also has books. Okay, so but I'll mention briefly the books. There is a book by Lin and Costello, which is probably available in cheap edition. Okay, so I think the first edition is available in cheap edition. You might be able to buy it. Okay, I think the title is Error Control Codes, if I'm not wrong. Okay, check on this. This is a good book to buy. Okay, it has enough information on it. The other books I've mentioned in the web page. Okay, if you go to the web page, you will see the syllabus and outline. The textbooks are listed there. Okay, so you can buy those. Most of the textbooks are expensive. It's in there. You have to pay like upwards of $100 for each of the textbooks. Okay, so if you don't feel like buying it, you have to rely on class notes, which means you have to attend every lecture. Okay, otherwise you will be lost. Okay, so that's about the textbook. And what else? Any questions about the administrative aspects, exams, grading, how is it going to work, etc.? No questions? Everybody is okay? All right. So looks like oh my god. Okay, so this thing is doing all kinds of crazy stuff. So let me see. Maybe this will work. Okay. All right. So if that is enough, then we'll start. Okay. Any questions once again? Anything on how it's going to be conducted? So the timings, I think, is I mailed people. So it's going to be Thursdays and Fridays, 3 to 5, in this place. Okay. So we'll have 2 lectures happening. I mean, kind of 2 1-hour lectures. Is the idea. We'll hopefully have a break in the middle around 4 o'clock for a few minutes, and we'll come back and continue. Okay, and anything else I'm forgetting, something that's usually said in the beginning of the class? No, it's okay. Okay, so let's begin. So this class will mostly be introduction. We'll also get started on some codes, but I would like to give a brief introduction to why coding is needed, etc. Okay, so 2 very popular engineering systems use error control codes as one of the key ingredients. Okay, the first one is, I think most people would guess very immediately, is communication systems, particularly digital communication systems. So those systems use error control coding. So that's the first application of error control codes. Okay, so in what way do they use error control coding is something that's of importance. We will touch upon it. So before we see it in great detail, I want to briefly mention how it works from a very high level. Okay, so how does a digital communication system look? So there are all kinds of pictures you can draw. So since it's an introductory class, I'm going to draw a picture, and then I'll ask you what it is. What is this? It's a cell phone tower. Okay, so it looks like that's the latest example you can give. Then what is this? Cellular phone. So obviously both of them are not to scale, just drawing it to something. Okay, so there's antennas here. Okay, antennas here, then there's an antenna here, and what you send out just eventually makes its way down to you. Okay, so important concern when you build a digital communication system is how do you reduce the power that you need to transmit 1 bit of information reliably, right? That's an interesting question you can ask. Okay, so what is the question again? Power needed per bit. Okay, so clearly I would like to decrease this, right? Why would I like to decrease this? Reduce power. That's the thing. I'm sure there's a nice name in mathematics for such kind of logic, but why would I like to reduce it? Yeah, battery is of course key, right? You can't just burn up the battery in 5 minutes. Then what's the point? You can't keep on recharging it. The point of being mobile is lost. and even on the base station end, even though you might have power, there are several situations where you might want to conserve power, right. You may not have power at some times, that happens a lot. Okay. So power per bit is an important issue. Okay. So it turns out if you do coding, you can get up to 9 dB improvement in power per bit. Okay. A 9 dB improvement is possible. Of course, this depends on specific type of channel, etc., etc. I am just giving you a 9 dB number. Maybe in your digital communication course you will learn more about how this works out. So this is a big number, 9 dB is a fairly large gain, 10 times reduction in power. Okay, so you have to imagine that. Okay, so this is the first application of error control coding. So by the end of this class, this course, you should know how this works. How is it that in a digital communication system you can get up to 9 dB of coding gain? What is the secret behind that? Okay, so with 1/10 of the power, how do you transmit a bit reliably? Okay, reliably is the keyword here. They have not mentioned it here. I guess you need reliability, right? You can't do anything. Another system where it is used very extensively is storage. Okay, so storage such as I am not going to draw a picture. This is one favorite picture of mine that I draw all the time. So let me draw it, just that one picture, and then I will not draw any more pictures. What is this? So some disk, DVD, CD, Blu-ray, whatever you want to call it. So this, or say a hard drive, right? Computer hard drive. So here the unit of interest is number of bits per let us say square inch. Okay. So this is the kind of metric that you want to optimize. So what would I like to do to this metric? It should be increased, right. So I want this to be as large as I can possibly make it. Okay. So there are obvious reasons why you might want to do it, but to give you a simple example, if you have a really long movie, the HD version you might want to fit it into 1 DVD as opposed to 10 DVDs, right. So that clearly depends on number of bits per square inch, and you might want to do that. Same thing with the hard drive. Today hard drives are in every device, they are in fact even in mobile devices, right. So you want to put as many bits as possible. Okay. And I do not have a similar 9 dB number here, but significant gains are possible by coding again. Okay. So the amount of improvement you can do because of coding in the number of bits per square inch is very, very significant in these two things. So if you take stock, just look around this room or anywhere you go, how many storage devices and how many communication devices do you think will be there? Okay. Yeah, so everybody has it, right. Everybody has a mobile phone, every room has like at least 2-3 computers in a university, or even at home you have computers. So the point I want to make is error control codes are everywhere. Okay, so they are one of the most ubiquitous piece of technology that you find anywhere you go in most systems. Okay, so of course communication is everywhere. Wherever there is communication, there is error control codes. Wherever there is storage, also there is error control codes. So you can't get rid of them whatever you do. Okay, so it's good to know. It's a nice technology to know. Okay, so this is a good picture. It looks very rosy and nice, but to really understand how codes work, you have to do a fair amount of mathematics. Okay, so it's an intense area. Okay, so you have to know how several things look. Okay, so after this we will plunge into some of that mathematics slowly, but anyway, so it's good to know in the first class at least that from a very high level it's nice to know about error control codes. Okay, so I'm not going to ask for any questions at this point because this is just too vague at this point. So we'll go to something more precise and then I'll pause for questions. Okay, so that's applications, and so I think this is probably the only slide where you'll have these kind of nice diagrams. Okay, so in case you're interested in modern art, might be keen on such things. Okay, so how does coding work? So here's a very, very simplified picture of how a communication system looks and how error control codes work in a communication system. Okay, so you might say, why am I saying communication system and why not storage system? It turns out storage also is like communication. Okay, so you write at one time and then you read at another time, right. So it's like a communication. So as opposed to happening at the same time at different points in space, you are at the same place, but you are reading and writing at different times. Okay, so both of them can be written down as communication systems, but that's what we will do in here also. Okay, so here's a very simplified model. once again to understand at the very high level what happens with error control codes. Okay. So, you have a channel, okay, which you are going to communicate. Usually I mean there is lots of digital communication signal processing that you have to do, a lot of engineering you have to do to work with a channel like this, but I am going to capture all of that in a very simple block diagram and simply say what, some modulator. Okay, so let us say I do not have enough space to write modulator here, so let me write it in 2 lines. Okay. So, this modulator is basically something which does signal processing to communicate into the channel. Okay. So, what error control codes do is you would have something called a encoder at the transmitter. Okay, hopefully you can see what I am writing reasonably all right. Okay, my handwriting is not the best in the world, but at least I think it is reasonably legitimate. Okay, there is not too much room for confusion. Okay, so the encoder sits at the transmitter. Okay, so this comes from some error control code. Okay, we have not seen what it is yet, but I want to show you how it fits into the system. Okay, some error control code which will define an encoder which is sitting in the transmitter. At the receiving end, at the receiver, okay, remember this is the transmitter. So, everything to this side is the transmitter. Oh my god, everything to this side is the transmitter. Likewise, everything to this side is the receiver. Okay. So, at the decoder you would do the opposite, you would have something called, at the receiver I am sorry, you have the decoder. See. So, this would undo whatever the error control code encoder did at the transmitter. Okay. So, this also plays a role here. Okay. So, what is the, from a very big picture point of view, what happens here? Suppose you have a message which is, let us say, some k bits. Okay. The encoder would do some coding and convert it into n bits. Okay. And this n typically would be greater than k, in most cases would be greater than k, and then these n bits would be sent on the channel. Okay. So, modulation is something which will do some signal processing to convert those bits into some signals which will go through the channel and they will be received on the other side, and you have to do a lot of processing also at the receiver. I am not showing any of that, I am directly putting down a decoder. Okay. So, you are going to do a decoding and you get back your message. Okay. So, you would get let us say an estimated message. Okay. So, I have just put everything at the receiver as decoder. Clearly, that is a very simplified view. You have to do a lot of signal processing before you can run a decoder. Okay. So, essentially what does an error control code do? Okay. It takes k bits and converts it into n bits, and you would have n as greater than k. Okay. So, let us see, if you just look at this, what is the encoder doing? Okay. Yeah, so there are lots of technical terms that people are throwing. For instance, one of the complicated ways of describing this is to say that it adds redundancy to the data. Okay, so it may not be very complicated, but it adds redundancy to the data. Okay, so once again, what is the point of adding redundancy? Remember my original motivation, I want to decrease the power per bit. Okay, so that is the motivation. Ultimately, this will reduce the power per bit, that is what we want to show. Okay, we will show that much later in the course, but that is the idea. This is how error control codes work. Okay, they would add redundancy to the bits that you are sending. Okay, and then so that finally the power per bit required after the redundancy is still lower than what it would have been without coding. Okay, so that is the idea of a coder. Okay, so if you have never seen how encoders look. This is how they would function in a digital communication system. Okay. So, you take your message which is k bits. So, you have to remember k is something like, let us say 1000 or something, put k there, imagine numbers like that. Okay. So, you have to imagine like that, and then n would be 2000, okay, something like that. Okay. So, it is a lot of bits. Okay. So, take that many bits, convert it into n bits. Okay. Usually, even though it adds redundancy, this will be a one-to-one mapping. Okay. Almost always, unless you want to do something very extraordinary at the transmitter, okay, this will be a one-to-one mapping. Okay. So, that is what the encoder would do. Okay. So, if you have to come up with an error control code, or if you have to design an error control code or specify an error control code, what should you do? What should one do? It is enough if you specify the encoder, right? Hopefully that is clear. I said the error control code specifies the encoder. So, if you specify the encoder, the operation is clear. I mean, how do you add the redundancy is all you have to specify. Okay. So, that is what we will see soon enough. Okay. How do you specify how this redundancy is added? Okay. So, that is the way you specify an error control code. And let me ask some quick questions based on just this encoder. Okay. How many possible messages are there? 2 power k messages, right? So, this one-to-one mapping will be from what to where? Where to where? 2 power k bit vectors to what? 01k to 01n. Okay, what do I mean by this? This is just fancy notation to say this is the set of all k bit vectors. Okay, so, it is the Cartesian product of 0 1 with itself repeated k times. Okay, so, if you do that, you would get the set of all k bit vectors. Okay, I have a one-to-one mapping from the set of all k bit vectors, which has to include all the k bit vectors, right? Yes or no? I mean, I can't just drop some message, right? If some message comes, I can't say I won't transmit it. So, I have to include all of them. So, how many vectors will there be in the range? 2 power k again. So, clearly it will not be what is called an on-to mapping. Okay. So, there will be vectors in 0 1 n which will not have a counterpart. Okay. So, that is what it means really to add redundancy. Okay. So, if you see this picture in a bit of a graphic notation, if I say this is 0 1 k, all the message here, all the points here are messages. Okay. After I do my encoding, what happens? I get a larger 0 1 n. What happens in the 0 1 n? I have once again a lot of points, but all these points are not really included. Only how many of them are included? 2 power k. Okay, so these are the range of encoder. Okay. So, this picture is a nice picture to keep in your mind. Okay, what does the code do? You said adds redundancy to the data. Okay, so after it adds redundancy to the data, how does the whole picture look? Previously, when you had no redundancy, you had the space 0 1 k and all the points in the space were being used. Now, after your encoding, you have actually a larger space 0 1 n in which you are not using all the points. Okay, how many points do you use? 2 power k of them you use. Okay. So, there is a very related definition which is called the rate of the code. What do you think is the rate of the code? K divided by n. Okay, so, this is the rate of the code, and typically rate is going to be less than 1 because n is greater than k. Okay, so, you have all kinds of rates. Okay, so, initially we are going to talk a lot about the encoder. So, as many of you can easily guess, the encoder is presumably an easier problem. Okay, what would be a more difficult problem? The decoding part of it would be more difficult. So, precisely for that reason we will look at decoders later. Okay, so, we will start with an encoder, and I will define a very simple encoder which is very commonly used. and then we will see how to study it properly. Is that okay? Any questions or comments at this point? Not really said much, but yes.
Total power rather than power per bit, because even though the power per bit has reduced, n is greater than k.
Oh, when I said total power, it's when I said power per bit, it's total power divided by total number of bits, total number of message bits, not coded bits. So to divide by k, that is still, that's the point. Okay, hopefully the question was clear. So you're saying power per bit. What if I divide by n as opposed to k? Is asking. Yes, if I divide by n, that's cheating. I agree. So you have to divide by k because k is the bits that you want to send. And after divide by k, it goes down. Okay. So once again, this picture, this simple graphical picture where you have this granular point fully being used as opposed to few points in a large space. It's a very important picture to keep in mind. It will recur again and again. Okay, so conceptually, it's easy to understand codes that way. Okay. All right. So what's the simple encoder that I'm going to describe? It's called a linear encoder. Okay. It's not the only way to encode. I mean, obviously, it's not the only way to encode. There are so many other ways of doing it. But for starting out, we'll look at what's called a linear encoder. Okay. So once again, like I said, we're going to look at the encoder in more detail in the beginning, and then we'll slowly move on to the decoder. Okay. So what does the encoder have to do? So it's going to take in k bits. Okay. So what does a linear encoder do? It's what it does. Let me just draw the picture. Okay. It has a message m. It sees a message m, which is from 01k, and it outputs. I never called the out. I never said what the outputs of an encoder are. The outputs of an encoder are typically called code words. Okay, so code word C from 01 n. Okay, so there are various ways of describing a linear encoder. So what I'm going to do is take a very simple description. So what a linear encoder would do is the following. Okay, so the message m is going to be k bits, right? So I'm going to call the k bits as m1, m2, so on till mk. All right. So what the linear encoder is going to do is going to compute the code word C by doing the following. It's going to take m1, multiply it by some vector which I'll call g1, and then to it will add m2 times another vector g2, so on till mk times another vector gk. Okay. So I have to tell you a lot of things. It's not done yet, but this is the general principle, and you can see why it's called linear. Okay, so it's linear because it's doing linear combinations of some fixed vectors. Okay, so that's why it's called linear. Okay, so this is an important principle to understand, but I have not explained what the GIs are. What are the GIs? GIs are from 01 n. Okay, so they are fixed vectors, which we can think of them as, say, basis vectors. Okay, so you can think of them as some kind of basis vectors, but these are some vectors that you pick ahead of time. Okay, all right. So then what else should I specify? Let me see. Nothing more needs to be specified. Everything is clear. What is m1 times g1 bar? What is that? What does that operation mean?
Scalar multiplication.
Scalar multiplication. Wow, so looks like people are far ahead of me, but anyway, so let me emphasize, say what that is. Okay, so each GI, like I said, is from 01 n. So maybe it is GI1, GI2, so on till GI what? N, right? So we can denote it that way, right? Each vector is like that. Okay, what is mi times gj? What is this operation? To each element of gj, I have to multiply by What is multiplication? It is just regular integer multiplication. Okay, think of the bits 0 and 1 as the integers 0 and the integer 1, and you are multiplying by the bit 0 or 1, which is again an integer 0 or 1. Just do integer multiplication. So basically 0 times 0 is 0, 0 times 1 is 1, 1 times 1 is 1 again. Okay, that is what you do. So this would be mij1, mij2, so on till mijn. Is that clear? So that is the multiplication. Okay, so if you are familiar with vector spaces, linear vector spaces over fields, and what this is, it's obviously the scalar multiplication in a vector space. So I have not come to that yet. We will see that slowly, but this is the operation that happens. Okay, the next operation is plus. Okay, what is plus? Okay, so I have to add, but then there is a problem here. I have already put it as equal to c. C has to belong to 0, 1, n. If I add 1 plus 1, what will happen? It will go to 2. So you are not supposed to do that. You are supposed to do all these additions modulo 2. Okay, so that is the next thing. So plus is modulo 2 addition. Is that okay? Alright, so it is like binary XOR. So 0 plus 1 would be 1, 1 plus 0 would be 1 again, 0 plus 0 is of course 0, but 1 plus 1 would be 0. So you get bits. Okay, so that is the idea behind this. Okay, so the entire encoder is specified by what in this scenario? The vectors G. Okay, so which you can think of as the basis vectors or the generating vectors, or the several names you can give to them. Those are the vectors which define the code C. So as you can imagine, your fundamental parameter of interest, the reducing the power per bit, etc., will totally depend on how you choose G. Okay, so if you choose G well, you get a good code, and then it will reduce your power. If you choose a very bad G, then nothing will happen. Okay, so that's as good as not doing anything. Okay, that's the idea. Okay, so this is what a linear encoder would do. Okay, I'm going to now write this operation in a slightly different way using matrices and vectors. Okay, which is a very common way of writing linear encoders. Once again, all this will be very simple if you have done linear algebra, but if you have not done it, it's worth seeing it. So essentially, what is happening is matrix multiplication. Okay, so you can think of the messages M1, M2, Mk multiplying a matrix which has what? Which has G1 in its first row, G2 in its second row, and so on, Gk in its last row. Okay. So once again, what is hidden in this multiplication is what? How I multiply 2 bits and how I add 2 bits, right? That is hidden in this multiplication. What am I supposed to do? Everything is done treating zeros and ones as integers, but modulo 2. Okay, that is the main thing to keep in mind. Okay, so everything is done modulo 2. Okay, so whenever I deal with bits and do multiplication and addition, this modulo 2 will almost always be implied in this course, and I will not write it too often. Okay, so I will assume you are familiar with, when you have done digital systems and courses like that, and you would know what it means. Okay, is there any question on this notation? It's okay, right? Alright, so this is done modulo 2. Okay, alright, now I am going to ask a very difficult question. Okay, so it's a particularly difficult question in this class, and already people are expecting a difficult question. Okay, how many code words will I get if I do this? If I take all possible 2 per k here, how many code words will I get? How many distinct code words will I get? Will I get 2 per k distinct code words always? What if I take all these vectors as 0?
Independent.
So you are assuming a lot when you say 2 per k, right? Or you are assuming something when you say 2 per k. Okay, so you should be aware of what that assumption is. Okay, so if you know linear algebra, this will be easy enough, but if you do not know, this is something to work out. Okay, so if I vary this M1 through Mk through all 2 per k possibilities, under what conditions will I get 2 per k code words? Yeah, so if all these vectors are linearly independent, okay, so how do you guarantee, how do you check that these k vectors are linearly independent or not? What should you do to compute the rank? How do you compute the rank? Okay, so you have to reduce it into whatever row reduced echelon form. How do you do that? What is the crucial step? Gaussian elimination. Okay, so it turns out you can do an operation of combining the rows in a clever way, which is called Gaussian elimination. It does not change the rank, okay, it does not change the dependence properties. So you keep doing it, you will get to this. Remember, once again, when you do Gaussian elimination, how will you add? You have to add modulo 2. Okay, so that is a twist in the process. Okay, if you are not used to doing Gaussian elimination modulo 2, it will confuse you a little bit. You may not have done it before. Okay, so we will maybe see some examples later on, but the thing I want to point out is, once you decide your vectors g1 through gk, you can do Gaussian elimination and figure out how many of them are linearly independent and how many of them are linearly dependent on the rest. Okay, so based on that, you can find what is called the rank of the matrix. Okay, the rank, once again, by standard linear algebra you can show will be at most what? At most k. Okay, it will be, it can be equal to k, it can never be greater than k. So that will be the rank. Okay, so if the rank is k, then what will you get? You will get 2 power k in different code words, okay, distinct code words. If the rank is less than k, what will happen? You will get 2 power rank of k, rank of g. Okay, so if this entire matrix is called G, okay, so if you denote this matrix as G, in fact such a matrix is very popular that it is called in fact the G matrix. Okay, so you can call it the G matrix. It is called what is called the generator matrix for the code. Okay, generator matrix G. It's a, I mean, we'll maybe define this later on, but it's good to know that this is called the generator matrix G, and the rank of G clearly plays a important role. Okay, what role does this play? Rank of G, 2 power rank of G equals number of distinct code words. Okay, so just purely based on intuition, when you pick G as a k by n matrix and you want to send k bits, you should pick rank of G to be k. Okay, so if you pick rank of G less than k, clearly you are giving up in the beginning itself. I mean, there are making too many errors and you will not get anything significant out of it. Okay, so usually rank of G is equal to k. Okay. Okay, so all right. So our code words for a linear encoder are code words C are generated by m times G, where this G is a k by n matrix, which is called a generator matrix. Okay, so this is the idea of a linear encoder. Okay, so this is a good thing to remember. So I can, for instance, make a picture like this. I draw M, and simply put G here and get a code word C. Okay. So this is the generator. We haven't. So one of the main aspects of this course is how do you pick this G. Okay, so code design can be reduced to the problem of picking a suitable G. Okay, so at this point, the good question to ask is, are we giving up anything by restricting ourselves to linear encoders? Okay, so that's a good question to ask. We will postpone that question as far as this course is concerned. We will pretty much look at only linear encoders. if you have taken information theory, or maybe if you read enough about information theory or some other course like that, there people show that linear encoders are good enough for almost all situations. Okay, so it is enough to look at this special type of encoders, they are quite good for communication purposes. Okay, so almost all purposes linear encoders are more than good enough. Okay, so we will exclusively see such things. Any questions? Okay. Okay. So I want to show you some examples, but before that we will introduce one more idea, which is fairly important. It makes the examples much easier. Okay. So there is something called a systematic encoder. Okay, so like I said, in this course we are only going to talk about linear encoders, so I will drop the term linear. Okay, so just assume that it is linear. So there is something called a systematic encoder. In the systematic encoder, what you do is you pick G as follows. Remember, G is k by n. You pick G as ik, where ik is what? It's, as you can guess, it's the k by k identity matrix. Okay, these are just dots, these are not ones and zeros, just separators. Okay, and then you would have a matrix P, which is what? What would be the dimensions? K by n minus k. Okay, so this is the generator matrix in systematic form. Okay, so this is systematic form. Okay, so that is why it is called a systematic encoder. Okay, so all these terms are used interchangeably. Okay, so this is the generator matrix in systematic form. Okay, so one thing that this does is, what is the one immediate simplification when you have a generator matrix in systematic form? Yeah, rank is k. I mean, you just don't worry about rank anymore. Okay, so otherwise you have to worry about doing. So this is also the row reduced echelon form kind of thing. Okay, so it's like that. So the rank is immediately obvious from the structure, it is k, so you don't worry about it. What is the other thing that you can notice from the systematic form? First k bits of each code word will be equal to m. So that is the other idea which is interesting. So in the systematic encoder, C, when you multiply m with G, will take the form m multiplied by ik, which would be m itself, and then m multiplied by p. Okay. So this is called as a systematic form for the code word. Okay. So one nice thing which we will maybe eventually see after a few examples is that any code, any linear code can be put into systematic form. Okay, so you are not losing anything by doing systematic. So that is the first thing which is very nice. So it is a very simple property, you can easily do that, which you do by row reduction, which is very easy to prove also, so you can see. Okay. So we are not losing anything by doing systematic, any code can be put in systematic form, so that is not a problem. But systematic form is also particularly nice from so many other points of view in practice. Okay. And for practice in signal processing and all that, systematic form is really nice and useful. Okay. So that is why, that is another reason why it is used a lot. Okay. So for one, yeah, so maybe we will see that later on, but it is useful in practice. Okay, so almost most of the codes that you will see out there will be in systematic form as it is being implemented. Okay, maybe there are very few exceptions, maybe one or two here and there, which might be in non-systematic form. Most codes would be in systematic form. Okay, so in systematic form, every code word will have a message part, and then the remaining part is called parity. Okay, so this is called the parity part. Okay, so the message part would be k bits and the parity part would be n minus k bits. Okay, so once you write the linear encoder in systematic form, you can think of the linear encoder as explicitly adding redundancy to your data. Okay, you have the message which comes out by itself, and then you add n minus k parity bits to the data. Okay. How are the parity bits formed? Why are they called parity? The parity bits are formed by, okay. Okay, so maybe at this point it's not clear to you immediately why it is called as parity. So basically this m times p, right, while we have written it like this, is actually selecting some subset of the bits in m and doing the XOR of all of them. Okay, so we will see that in an example and then it will become more clear later. Okay, so that is why it is called parity. You are taking subsets of the message bits and doing parity of that. Okay, that is the idea there. Okay, so let us see example in systematic form, then we will see an example in non-systematic form and reduce it to systematic form. Okay, so that is the two things we will try. Okay, so the first example, we will take G as 1 0 0 0 1 0 0 0 1, then I have this fictitious separator which is clearly not the part of the matrix, I am just doing it as separator, 1 0 1 1 1 0 0 1 1. Okay. So what are the various things you can infer by looking at this generator matrix? Systematic, okay. What are the other parameters that are of interest to me? Sorry, k is 3 and n is 6, okay, good. Some people have figured out what I want. Okay, so what I want is a very simple observation. So you observe that k equal to 3 and n equals 6. So in particular the rate is going to be, okay, rate is denoted r several times, so I will say rate r equals 1 by 2. So it is a rate half code. Okay. So one good thing to do always is to list all the code words of a code. Okay. Particularly for small codes you can do that. If k is very large, it is very difficult to do that, so we will not do that, but for small k it is good to list all the code words of the code. Okay. So remember my picture where I drew a circle with all the 3 k bit vectors and then the code words as a subset of the points in the n bit vectors. Okay. So it is good to draw that a couple of times and see what is actually happening when we do something like this. Okay. So we will do that here for this simple example. We may not do it later on, but it is good to do that once to see a list of all the code words. Okay. So let us make a table. The table will have 2 columns. First column will have all possible messages, then next to it we will write all possible code words. Okay. So one nice thing to help you do this is to first write how the code word is formed in the general case. Okay. Suppose you have m as m1, m2, m3. Okay, what will be the corresponding code word? It is going to be m1, m2, m3. Okay, that was easy enough. How will the fourth bit be formed? It is m1 plus m2. Okay, it is good that everybody says m1 plus m2 because by now we are used to the mod 2, right. So you do not have to say XOR, it is just m1 plus m2. What will be the fifth bit? m2 plus m3. What will be the sixth bit? m1 plus m3. Okay. So now I guess my previous comment about why it is called parity is a little bit more clear, right. What is happening to the parity bits? How are the parity bits produced? You pick a subset of the message bits and then do the XOR of them. Okay. So how are the subsets specified? Specified by the columns of P. Right. So wherever the ones are ones in the columns of P tell you which bits are getting XOR. Okay. So it is a very simple operation, but all these things are good to keep in mind. Sometimes it will help you visualize what is happening. Okay. Okay. So I will give you a couple of minutes. Why don't you go ahead and fill out all the message and code word pairs. It is quite easy to do, but it is good to do. Okay, so hopefully there are no major surprises in this list. So as you can see, there are 8 messages. Okay, all 8 3-bit vectors are messages, and then how many code words do you have? 8 of them. All of them are distinct. Okay, what did I do? 001. Oh my goodness, thank you. Okay, so there are only 8 code words. Okay, so how many total 6-bit vectors are there? 64. Okay, only 8 of them are code words. Okay, so you have a lot of room. Okay, so that's the redundancy that people talk about. Okay, so you just use 8 possible 6-bit vectors out of this huge 64 possibilities. Okay, so there's lots of redundancy there. And what else can you observe from here? Okay, so I think I didn't want to say anything more beyond this. So this example is probably clear enough. Okay, so we'll come back maybe and see more properties of this later on. Okay, for now this example is okay. Any questions on this example? How we got it, etc. Okay. Okay, so the next one is a G which okay, so I'm going to give a slightly more complicated example because okay, what have I done here? Does it remind you of something you must have done in your digital systems course? You must have written down something like this when you made truth tables, right? So it's just listing out all possibilities in a different angle, that's all. Done it from left to right, and finally I've added all ones just to complete things. Okay, so what is K and N for this? Okay, so 4 you have to be a little bit careful, you know. I mean, the reason is usually you want to take K to be rank of G. Okay, so once you know that the rank of G is 4, then you can say 4. Okay, otherwise it's always good to take K to be equal to rank of G. You don't want to take something greater than K. Okay, N is clearly 8, I agree. K in fact is 4 for this problem, but you should find the rank explicitly before you can be sure. Okay, all right. I'll give you a couple of minutes to get used to this, but then we'll quickly see the row reduced form and see how it works. Okay, this is G. K we will determine. Okay, so the row operations, I mean you have to do quite a few row operations here, right. So the first thing to keep in mind is you have to bring a 1 to the first position and then eliminate all the other ones. So here you have to bring the 1 to the first position, what should you do? Swap the last column with the first column. Okay, then you don't have to do anything else, right. And then what do? Get a 1 to the second one and then do some additions, row operations. It's a series of steps and I would highly recommend that all of you try this. Okay, so you go back tonight in the evening and then try it. Okay, so it's quite important if you haven't seen something like this before. Okay, so it can confuse you a little bit. Okay, so a couple of things to keep in mind is you can do any number of row interchanges when you do this operation, nothing will happen to the code, but if you are forced to do a column interchange, what will happen? Yeah, something will change in the code, right, the code will change, but from an error control code point of view, from a communication system point of view, it does not make any difference. Why does not it make any difference? It only changes the order in which the bits go out, Okay, so usually what happens is column swaps are also allowed when you do this Gaussian elimination. So you can do column swaps as long as you remember that the sequence of bits going out has now changed. Okay, so it's okay. So to reduce it to systematic form, you can do row operations definitely, but you can do column swaps. But what is it that you cannot do? You cannot add two columns. Okay, so that doesn't make much sense from a Gaussian elimination point of view. Okay, adding two columns is definitely not allowed. Okay, you cannot do that. Okay, so an exercise for you is to convert it into systematic form. Okay, so you will see k equals 4, then you try to list it out, you will get 16 different code words. Okay, there will be quite a few of them. Okay, so you can try to write down if you like. Okay, but this is a good exercise to figure out how to find systematic form for the code, for the generator matrix. Okay, so any number of examples you can now come up with, it's not too difficult. So this one is a particularly famous code, it's a very famous code, we will maybe come back and see it later. Okay, so the previous one had nothing very special about it, but this one has, well, maybe the previous one also has something special about it, but this one is quite special. Okay, so it's got lots of history. Okay. Okay, so I'm going to pause for about 4 minutes. We will commence again at 4:10. Okay, you can't